The DES, or Data Encryption Standard history, started in 1972 when a National Bureau of Standards study of U.S. government computer security identified a need for a government-wide standard for encrypting unclassified, sensitive information. Around the same time, engineer Mohammed Atala in 1972 founded Atala Corporation and developed the first hardware security module, or HSM, the so-called Atala box, which was commercialized in the year 1973. It protected offline devices with a secure pin-generating key and was a commercial success. Banks and credit card companies were fearful that Atala would dominate the market, which spurred the development of an international encryption standard, or IES. Atala was an early competitor to IBM in the banking market and was cited as an influence by IBM employees who worked on the DES, or DES standard. Moreover, the IBM 3624 later adopted a similar pin verification system to the earlier Atala system. On May 15, 1973, after consulting with the NSA, NBS solicited proposals for a cipher that would meet rigorous design criteria, but none of the submissions was suitable. Then a second request was issued on August 27, 1974, wherein this time IBM submitted a candidate which was deemed acceptable. A cipher developed during the period 1973 to 1974 was based on an earlier algorithm, Horst-Feistel-Lucifer cipher. The team at IBM involved in the cipher design and analysis included Feistel, Walter Tuchman, Don Coppersmith, Alan Conham, Carl Mayer, Mike Mathias, Roy Adler, Edna Grossman, Bill Nuts, Lynn Smith, and Brian Tuckerman.
What is the DES? DES stands for Data Encryption Standard, were developed in 1977. It is a multi-round cipher that divides the full text into two parts and then works on each part individually. It includes various functionalities such as expansion, permutation, and substitution, XOR operation with round key. DES is a block cipher and encrypts data in the blocks of size of 64 bits each, which means 64 bits of plain text go to as the input to DES, which produces 64 bits of ciphertext. The same algorithm and key are used for encryption and decryption, with minor differences. The key length is 56 bits. The basic idea is shown in the figure.
DS stands for Data Encryption in Standard. The date of creation is 1977. Bit-oriented. Key length is 56-bit in DES. DES involves 16 rounds of identical operation. Structure is based on the Feistel network. The design rationale for DES is closed. The selection process of this is secret. DES can be broken easily as its known vulnerability. The rounds in DES are expansion, XOR operation with round keys, substitution, and permutation. DES can encrypt 64 bits of plain text. It generates ciphertext of 64 bits. Cipher is derived from Lucifer cipher. DES was designed by IBM. Known attacks against DES include brute force, linear cryptanalysis, and differential cryptanalysis. It is slower than AES. It is not flexible. It is efficient only with hardware.
Example of how to encrypt data using DES. Example, let M be the plaintext message M equals 0123456789ABCDEF, where M is in hexadecimal base 16 format. Rewriting M in binary format, we get the 64-bit block of text. The first bit of M is 0. The last bit is 1. We read from left to right. DES operates on the 64-bit blocks using key sizes of 56 bits. The keys are actually stored as being 64 bits long, but every 8 bit in the key is not used. However, we will nevertheless number the bits from 1 to 64, going left to right in the following calculations. But, as you will see, the 8 bits just mentioned get eliminated when we create subkeys. Let k be the hexadecimal key k equals 133457799 BBCDFF1. This gives us the binary key setting 1 equals 001, 3 equals 0011, etc. And grouping together every 8 bits, of which the last one in each group will be unused. Step 1. Create 16 subkeys, each of which is 48 bits long. The 64-bit key is permuted according to the following table, PC-1. Since the first entry in the table is 57, this means that the 57th bit of the original key K becomes the first bit of the permuted key K+. The 49th bit of the original key becomes the second bit of the permuted key. The fourth bit of the original key is the last bit of the permuted key. Note, only 56 bits of the original key appear in the permuted key. Example, from the original 64-bit key, we get the 56-bit permutation, which is the K plus. Next, we split this K into left and right halves, C and D, where each half has 28 bits. This is an example from the permuted key K plus. This is what we get. So with C and D defined, we now create 16 blocks where n is less than or equal to 1 and 16 is less than or equal to n. So each pair of blocks C and D is formed from the previous pair C n dash 1 and D sub n dash minus 1, respectively for the n equals 1, 2, to 16 using the following schedule of left shifts of the previous block. To do a left shift, move each bit one place to the left except for the first bit, which is cycled to the end of the block. This means, for example, C sub 3 and D sub 3 are obtained from C sub 2 and D sub 2, respectively by two left shifts, and C sub 16 and D sub 16 are obtained from C sub 15 and D sub 15, respectively by one left shift. In all cases, by a single left shift is meant a rotation of the bits one place to the left, so that after one left shift, the bits in the 28 positions are the bits that were previously in positions 2, 3 to 28, 1. Example, from the original pair C sub 0 and D sub 0, we obtain this. So we now form the keys k sub n for 1 is less than or equal to n is less than or equal to 16, by applying the following permutation table to each of the concatenated pairs C sub n D sub n. Each pair has 56 bits, but PC-2 only uses 48 of this. Therefore, the first bit of k sub n is the 14th bit of C concatenated C sub n D sub n. The second bit of the 17th and so on, ending with the 48th bit of k sub n being 32 bit of C sub n D sub n. For the first key, we have C sub 1 D sub 1 is equal to this, which after we apply the permutation, PC-2 becomes like this. So for the other case, we have this from K sub 2 to K sub 16. So much for the subcase. Now we look at the message itself.
Next, after we created 16 subkeys, we are now in step 2, which is to encode each 64-bit block of data. So there is an initial permutation or IP of the 64 bits of the message, data, M. This rearranges the bits according to the following table, which were shown below, where the entries in the table show the new arrangement of the bits from their initial order. The 58-bit of M becomes the first bit of IP, the 50th bit of M becomes the second bit of IP, and the 7th bit of M is the last bit of IP. Below is the previous message we got and the initial permutation or IP of the message through the table were displayed. So here, the 50th bit of M is 1, which becomes the first bit of IP. The 50th bit of M is 1, which becomes the second bit of IP. The 7th bit of M is 0, which becomes the last bit of IP. Next is to divide the permuted block IP into the left half L0 of 32 bits and the right half R0 of 32 bits. From IP, we get L0 and R0, which were shown below here in PowerPoint. Proceed through 16 iterations for 1 is less than and equal to n is less than equal to 16 using a function f which operates on two blocks, a data block of 32 bits and a key kn of 48 bits to produce a block of 32 bits. Let plus denotes XOR addition, bit by bit addition modulo 2. Then for n going from 1 to 16, we calculate. This results in a final block for n is equal to 16 of L16 R16. That is, in each iteration, we take the right 32 bits of the previous result and make them the left 32 bits of the current step. For the right 32 bits in the current step, we XOR the left 32 bits of the previous step with the calculation f. Example, for n is equal to 1, we have here that is shown below the K1 and the L1 is equal to RO equal in the bits, and last the R1 is equal to L0 plus F open parenthesis R0 and K1. It remains to explain how the function f works. To calculate f, we first expand each block Rn minus 1 from 32 bits to 48 bits. This is done by using a selection table that repeats some of the bits in Rn minus 1. We will call the use of this selection table the function e. Thus, e open parenthesis Rn minus 1 has a 32-bit input block and a 48-bit output block. So here, let e be such the 48 bits of its output written as 8 blocks of 6 bits each are obtained by selecting the bits in its input in order according to the following table. So this is the table, the e selection table. Thus, the first 3 bits of e, Rn minus 1 are the bits in positions 32, 1 and 2 of Rn minus 1, while the last 2 bits of e, Rn minus 1 are the bits in positions 32 and 1. So next, we calculate the e R0 from R0 as follows. R0 is equal to in the bits. Next, the e open and parenthesis the R0 is equal to 0, 0, 1, 1, 1, 0. And take note that each block of 4 original bits has been expanded to a block of 6 output bits. Next, in the F calculation, we XOR the output E, Rn minus 1 with the key Kn. Here, it was also shown below. For K1, E, R0 we have here also. To this point, we have expanded Rn-1 from 32 bits to 48 bits. Using the selection table and XOR the result with the key Kn. We have now 48 bits or 8 groups of 6 bits. We now do something strange with each group of 6 bits. We use them as addresses in tables called S boxes. Each group of 6 bits will give us an address in a different S box. Located at that address will be a 4-bit number. This 4-bit number will replace the original 6 bits. The net result is that the 8 groups of 6 bits are transformed into 8 groups of 4 bits. Note the 4-bit output from the S boxes for 32 bits total. Write the previous result, which is 48 bits in the form. So here they are. Kn plus E, Rn-1 is equal to B1, B2, B3, B4, B5, B6, B7, B8. So this is where each Bi is a group of 6 bits. We now calculate S1, B1, S2, B2, and so on. So this is where Si is equal, close and open parenthesis, Bi refers to the output of the THS box. So it was also shown here. To repeat, each of the functions S1, S2, or S2, S8 takes a 6-bit blocks as input and yields a 4-bit block as output. The table is determined. S1 is shown and explained below. So next, here in the table, if S1 is the function defined in this table and B is a block of 6 bits, then S1 or B is determined as follows. The first and last bits of B represent in base 2 a number in a decimal range 0 to 3 or binary 00 to 11. Let that number be a letter I. The middle 4 bits of B represent in base 2 a number in the decimal range 0 to 15, binary 0000 to 1111. Let that number be a letter J. So as we look in the table, the number in the ITH row and JTH column, it is a number in the range 0 to 15 and is uniquely represented by a 4-bit block. So that block is the output S1B of S1 for the input B. For example, for input block B is equal to 011, 011. The first bit is 0 and the last bit 1, giving 01 as the row. So this is the row 1. The middle 4 bits are 1101. This is the binary equivalent of decimal 13. So the column is column number 13. In row 1, column 13 appears 5. This determines the output. 5 is binary 0101, so that the output is also the same 0101. Hence, S1 close and open parenthesis 011 011 is equal to 0101 that was shown below. So the tables defining the functions S1 to S8 are the following here in this presentation. So for the first round, we obtain as the output of the 8 S boxes. So here, in the final stage in the calculation of F is to do a permutation P of the S box output to obtain the final value of F, where F, P, S1, B1, S2, B2 to S8 from the output of the 8 S boxes. So here, it was shown in the presentation. So we got here, it was shown below. The F is equal to, in the bits, R1 is equal to L0 plus F, R0, and K1. In the next round, we will have L2 is equal to R1, which is the block we just calculated, and then we must calculate R2 is equal to L1 plus F, close and open parentheses R1 and K2, and so on for 16 rounds. At the end of the 16th round, we have the blocks L16 and R16. We then reverse the order of the two blocks into 64-bit block. So here it is, the R16, L16. So we must apply a final permutation IP minus 1 as defined by the following table. That is, the output of the algorithm has bit 40 of the pre-output block as its first bit, bit 8 as its second bit, and so on, until bit 25 of the pre-output block is the last bit of the output. After that, if we process all 16 blocks using the method defined previously, we get on the 16th round, so here, the L16 and the R16, it was also shown here. So after that, we reverse the order of these two blocks and apply the final permutation to R16, L16, and the IP minus 1 also here. So next, which in hexadecimal format is 85E8135440F0AB405. So the results here, this is the encrypted form of message is equal to 012345678 ABCDEF, namely C is equal to 85E8 and so on. And so that's the example of how to encrypt data using DES with the step-by-step process.